Alrighty, everybody, here is your much anticipated Unit 4 Part 1 test review video key. I've completed most of it already, and I'll just go through and explain a lot of it, and some stuff I've left blank, which we'll talk about together right here. Alright, so first we got to do properties of exponents. Now, please keep in mind there are multiple ways to do these problems. I will do it the way that I think most students probably did it, except with the exception of number 1, because I think maybe students tried this a different way. But the first thing I noticed is all of this right here is to the 0 power. And remember, anything to the 0 power is equal to 1. So this actually equals h cubed, k to the first, which I don't need to write to the first, times 1. And then anything times 1 is just itself. The times 1 doesn't actually matter. And so you end up with this as your final answer. Number 2, now here we kind of call this, we say we distribute, but it's not really distributive property, but this power right here, since all this stuff is in parentheses, this power has to go to every term in here, including the 3. This 3 right here really has a power of 1 that we don't typically write. So all of this is called power to a power, because we have a power of 5 here, raised to a power of 3 here. When it's power to a power, you multiply the exponents. So I'm going to do that first. You could simplify all of this stuff first and then take care of that 3 later. But I'm going to use the 3 first and get 3 cubed. When you raise power to a power, you multiply the exponents, so it's 5 times 3. I'm going to do 3 times 3 for my y's. Z is 4 times 3 is 12. And do the same thing on the bottom. This negative right here has nothing to do with exponents whatsoever. It's just like a negative 1 right there, if you want to write that. So we have a negative number in front. And then we have y to the 9th, because again, we have power to this power, and then z to the 3rd. So that's our start right there. Then we can simplify some things here. 3 cubed is 27. 3 times 3 times 3. Then we have x to the 15th, and we have no other x's. So we don't have to worry about anything with that. Let's make that highlighter a little smaller. All right, so there's nothing else with x, so we're good there. Now we have y to the 9th and that y to the 9th. And so there's, when you divide two things that have the same base, so they both have a base of y, you subtract the exponents. So you end up with y to the 0, but y to the 0 is 1. So this turns into 27 times 1, which we don't need. We also have this x to the 15th there. And you don't need to write times 1. Then we have z to the 12th divided by z cubed. Again, subtract your exponents, and you get z to the 9th. Now we still have this negative down here, so we're dividing by like negative 1, because remember that's actually like a negative 1 right there. Right? So dividing by negative 1, though, is the same as just having your answer be negative. So that's our final answer to that problem. Number 3, whenever there's a big fraction like this, I like to do everything in the top first. I'm going to simplify all that stuff. And then I'll simplify the bottom separately. Then I'll take care of that, like combine those. So we have, I'm going to go through and highlight my variables that are the same. We'll take care of that stuff first. All right, so first in the numerator, we have a to the 5th times a. So we have 5 a's here times 1 more a, so we have 6 a's multiplied together total. So a to the 6th. Or you might remember you add your exponents in this situation. So here we're going to do 6 power plus negative 2, giving us b to the 4th. Then we have c to the negative 2, c times c to the 4th, so you add those exponents, giving us c squared. All over. Now this is like what we did on the last problem. You take this negative 2 and you multiply it by that number and by the number right there, which remember there's an invisible 1 that we don't write. So on the bottom we get b to the negative 4th, c to the negative 2nd. Now remember how negative exponents work. It really just means that they're on top. Or if there was a negative exponent up here, that means that thing's on the bottom with positive exponents. So it's really a to the 6th, b to the 4th, c squared. And then this b to the 4th goes to the top. And the c squared, this one goes to the top as well. And so now we again can do this thing where we have two things that have b, so we can multiply those together. We've got two things that have c, so you multiply those, but when you multiply, you actually add the exponents. So you end up with a to the 6th, b to the 8th, c to the 4th. Okay, so remember, a negative exponent just kind of switches the location. If it was in the bottom already, you move it to the top, and if it was in the top already, you move it to the bottom, and then make your exponent positive. Okay, so now we're going to name these things, classify the following polynomials. Classifying kind of means like name it. So this is a quadratic because our highest degree is 2. And then it's a monomial because there's only one term. So this is based on the exponent. This is based on how many terms there are. So then we have a quartic because a degree of 4. And there's two terms, which is a binomial. And now we have a cubic because the highest exponent is 3. But there's 4 terms. Once we get to 4 or more terms, we just call it a 4-term polynomial. Or if there were 6 terms, you would call it a 6-term polynomial or whatever. Okay, looking at this graph. So I have it all answered, but I'll explain it. So remember, as x goes to negative infinity, just means as you look to the left. So as the graph goes left, which way does it go, up or down? And you can see it's going down, so it goes to negative infinity. This means as x goes to the right, so as x goes to the right, which way does the graph go? It's going up, so it goes to infinity. We know it's an odd degree because our end behaviors are opposite. One side goes down, one side goes up. It doesn't matter. It could go up on this side and down on the other side. We still know it's an odd degree because the end behaviors are opposite. We know the leading coefficient is positive because the graph is going up forever to the right. Okay? How many zeros does this function have? Well, the zeros are x-intercepts, so I've highlighted them here in orange already. We have 1, 2, 3 zeros, or 3 x-intercepts. And then I already highlighted them in orange. It says circle, I highlighted. Okay, number 8, the degree of the function. So this, imagine you multiply all this out. Now, but we only have to look at the x's because that's going to determine our degree. So if I multiply this and I actually square it, I'm going to end up with x squared times another x here is x cubed times another x here is x to the 4th. Or you can just add these powers. There's a 2 there plus that 1 plus a 1 right there. And so 2 plus 1 plus 1 is 4. Since the degree is 4, we know the end behaviors are going to be the same. They're either both up or both down. In this case, I know they're both infinity because our leading coefficient is positive. Here we have a positive x. You square it anyway, so even if this one was negative, it would turn out positive. Times another positive is positive. Times another positive is positive. So since our leading coefficient is positive, we know that it goes up to the right. And since it's an even degree, our end behaviors are the same, so we know it goes up to the left. Y-intercept, you plug in 0 for x's, and then evaluate this. So you plug in a 0 here, so that's just gone. You get 1 squared times negative 1 times negative 2, because those x's are zeros, and you get 2. And then the zeros themselves are whatever makes this 0, whatever makes this 0, whatever makes this 0. So you get negative 1, 1, and 2, which I've written here. And then the multiplicities is like how many times each 0 or each factor occurs. This factor occurs twice because of that power. So it has a multiplicity of 2. This has a multiplicity of 1 because there's really a 1 right there. And we have a multiplicity of 1 because there's a 1 right there. And that's where these multiplicities come from. And then remember, based on the multiplicity, it tells us if it's an even multiplicity, the graph passes or bounces off the x-axis at this 0 and turns around. At these zeros, since the multiplicities are odd, the graph's going to pass through. So this graph is going to look roughly like this. So we know it's going to go up forever in both directions, so it's coming down from over here. It's got to bounce off here, go up to our y-intercept, and we don't really know where it turns around, but it's got to turn around before it gets to this next x-intercept. Oops. And we know it passes through that x-intercept, and then it has to turn around and pass through the other x-intercept, or 0, and now we have our end behaviors correctly. They're both going up. So that graph looks roughly like that. I have this in Desmos right here, so we can see what it looks like on Desmos. And if we put it side by side, we'll see how close we actually were. I mean, that's pretty close to looking the same right there. So that's pretty good. All right, and then number 9, same kind of question. Our degree is going to be, there's actually a 1 from this, because this is x to the first. Then you have another first power right here, so that's 2, plus 3 more here would give us 5. So our degree is 5. That tells us our end behaviors are automatically opposite. So to determine as x goes to the infinity, or as the graph goes to the right, look at the leading coefficient. This one's negative, times a positive is negative, times another positive stays negative. So we have a negative leading coefficient. So as the graph goes to the right, remember that just means goes to the right, it's going to go down forever because our leading coefficient is negative. Since it's an odd degree, our end behaviors are opposite. So since we've determined that to be negative, this one must be positive. Y-intercept, again, is when x is 0. So if you plug in 0 for this x right here, you get 0 times whatever else is over here. It doesn't even matter. You're going to get 0 because we're multiplying by 0. So our y-intercept is actually 0, 0. Our zeros, or our x-intercepts, you're going to get one from this. What value do you plug in for x right here to get 0 right there? Well, 0. If x is 0, you get 0. So x equals 0 is one of our zeros, and it has a multiplicity of 1, because this has a power of 1 right there. Then we get negative 3 with a multiplicity of 1, and we get positive 2 with a multiplicity of 3. So all of these are odd multiplicities, which means the graph will pass through every single one of these zeros. And we know that it's going to go down from this direction. Sorry, as x goes to negative infinity, it goes up forever. So yeah, so we know it's coming down like this, passes through. It's got to turn around somewhere, pass through there, turn back around and pass through one more time. And so we have opposite end behaviors. And again, I have this graphed already. Oh, on Desmos, which is this one, I think. And then let's see. And so you can see it's pretty close. Right around here, I didn't really get the shape right, but I'm not concerned with that. Again, we don't really know how high it goes. And like this part where it kind of flattens out, we're not concerned with that for now at least. There are ways to figure that out, but not what we're doing right now, so it's okay. So just a basic sketch, and so it does look something like that at least. Really, it gets flatter the higher this is. So I should have flattened that out a little bit, but we haven't talked about that, so that's okay. All right, direct substitution, evaluating f of negative 2. That just means plug in negative 2 up here. I've shown my work. I did not write the answer, though. So you plug in negative 2 everywhere. And then this one is negative 2 squared, which is 4. But then you have another negative in front. So that actually comes out to be negative 4 minus 12, because 6 times negative 2, and then minus 5. So that should get us negative 21 when x is negative 2. And then using synthetic substitution, I've already set it up. Now we're plugging in a different number. So whatever number you're plugging in goes over here, like in that little box. These are the coefficients, negative 1, 6, and negative 5. Now remember, if this wasn't here, and it just said negative x squared minus 5, you have to put a 0 for any degrees that are missing. So start with the highest one and count down. And if any of them get skipped, you got to put a 0 in here. But to do this, you bring down the first number, which is negative 1. And now you multiply these two. And so you get negative 3, and you write it in the next spot over. Add these two, and get 3. And now multiply again to get 9. And add again right here to get 4, and that is the final answer. So if I plug 3 into this function, I will get 4 just like I did it here. And that is it.